Packing fraction concept was proposed by the scientist Austin. Here actual isotopic mass minus mass number into 10 power 4 by mass number. Its value depends on the manner of packing of nucleons within the nucleus. It may be negative, positive, even zero. Zero case, this is zero. So its mass number is 12, actual mass is 12. So the value of actual isotopic mass number depends on the conversion of the mass into energy, binding energy. If it is negative, the actual isotopic mass is smaller than the mass number. So in such case, energy is released during the formation of nucleus. The graph looks like this. This is the packing fraction. This is the mass number A. It is a negative, positive. This is around 180 mass number. And beyond that, unstable. These are medium mass number nucleus are stable. Most of the transition elements are stable. The packing fraction concept explains the relative stability of medium mass number nucleus and higher mass number nucleus. They are found to be unstable and found to be radioactive. These are found to be stable. And again, it fails to account the relative stability of lower mass number nucleus. Third aspect of nuclear stability is the N by P ratio. As we know that up to the atomic number 20, proton number is equal to the neutron number. After 20 atomic number, neutron number increases as the atomic number increases. And here, if you really draw proton versus neutron, up to 20, straight line, linear relationship, beyond that increases. And many elements have the isotopes, hence a zone can be explored. This is up to the 20, atomic number 20. This is called zone or belt of stability. N by P versus P, like this. Thus clearly indicates that proton number increases, means atomic number increases. The N by P ratio goes on increases. This will go up to the level of 1.6. Now what is found that above this and below this zone of stability, they are found to be unstable. In fact, they are found to be radioactive elements. And they tend to fall into the zone of stability while disintegrating the nucleus, and also the nucleus which fall below the zone of stability, they tend to fall into the zone of stability by undergoing various nuclear processes. Now we can see two different processes of nucleus having high N by P ratio and low N by P ratio. One, high N by P ratio nucleus. In the high n bipedation nucleus, neutron number must be decreased and proton number must be increased, or both simultaneously. Neutron transforms into the proton and electron, neutrino. This is the one of the nucleons resulted in the unstable nucleus. Example here, the C14-6. Here neutron number is decreasing. Here 7 nitrogen, 14 this is the electron and neutron. This electron which is coming out called beta particle. So by the emission of beta particle, stability is attained. They fall into the zone of stability. You can see the n-bip ratio. 1 n-bip ratio is more than 1. More than 1. Many examples can be given. Sodium 24, 11. This is the 12, magnesium 12, and aluminum 29, 13, 14, silicon 29. So the stability is attained. This is the daughter nucleate. Daughter nucleate stability is attained while emptying the beta particle from the parent nucleate. We can see the barium. Barium 56, 141. Beta particle is emitted. 58, that is the lanthanum 141. One more beta particle. This 57. This is 57 is the lanthanum. 58 is the cerium 141. 59 is the praseodymium 141. So the successive emission of beta particles. Here to here stability is gained, and further stability is gained, still further stability is gained. That can be visualized in terms of the T off. Here the T off half-life period is just 1.8 hours. This is this half-life period is 3.7. This is 1.8 minutes, hours, 2.8 days. 2.8, 28 days. So that's how the stability is gained by the successive emission of the beta particles. Now the low n-bip ratio. Low n-bip ratio nucleates, various disintegration processes are understood. So that is, in order to fall into the zone of stability, neutron number must be increased or proton number must be decreased, or both simultaneously. For example, neutron capture and proton emission. You can give this example: 30, 64, neutron capture, and 29, proton is emitted, copper 64. And proton emission. polonium 21284, proton is emitted. Here the 82, lead to 11. See that here from year to year stability is gained and vapor ratio is improved, and here the isobond is resulted in this process. Here isotone is resulted, same number of newtons. Next is the positron emission. Positron emission takes place when proton splits into this antineutron. This is one of the nucleus which is unstable, which is resulted during the interaction of proton and neutron. Proton transforms into the neutron and positron. This is the positron is the antimatter of electron. Generally, matter antimatter collides, annihilation takes place, mass destruction takes place. So example C611. Now this proton, it becomes 5 boron 11 positron. So isobond is resulted. This is the same number of isotone is resulted here. So proton is isotone is resulted, same number of neutrons. And one more very important phenomenon is the alpha emission. Most of the heavy nuclears emit the alpha particle. Means when alpha particle is emitting means they fall below the zone of stability of the graph. Best example, as you know, 238, 92, 90, thorium, 234 alpha particle. As I explained earlier, the relationship between the parent and daughter nuclei by isodiaphoric relationship, that is the equal difference between the neutron and proton, earlier which I explained. And very rare thing is the K-shell electron capture. Here electron, proton, this is present in the K-shell, first shell, and the proton within the nucleus, resulting to the neutron. This was found in potassium 40, and here proton is 18, becomes argon and 40. Generally, once this is resulted from this nucleus, gamma rays are emitted. Here, this is the again form of the isobond formation. Now, in the high n-vapor ratio, isobond is resulted during the emission of the beta particle. Now we discuss the low n-vapor ratio, different nuclear emission take place, different nuclear process, which may be the neutron capture proton emission, or proton emission, or positron emission, alpha emission, K-shell electron capture. In all these cases, relative stability of the daughter nuclei increases, they fall into the zone of stability, n-vapor ratio is improved, ultimately fall into the zone of stability. The stability, relative stability of different nuclears can be explained from this different nuclear process. Next one is the nuclear shell mode. Nuclear shell mode. And magic numbers. You know, 1s2, 2s2, 2p6. It is the 2 is the maximum capacity of first shell, that is K shell, in terms of electrons. L shell magazine capacity is 8 electrons. And 3s2, 3p6, 3p10, 18 with respect to the KLM shell. And these are set up the magic numbers with respect to the electrons to explain the relative stability of the atoms. Similarly, same type of magic numbers are resulted within the nucleus to explain the stability. And those are the proton or neutron number with respect to the numbers 2, 8, 20, 28, 50, 82, 126, recently 114, 164, 184 correspond to the magic numbers. Say for example, this nucleus stable, either proton or neutron number, and oxygen 8 and 16 proton and neutron number, calcium 20 and 40 proton and neutron number, and 28 say tin 50 118 with respect to only proton number, and lead 82 208 82 is the proton, 82 is the proton number, and whereas 206 minus 82 is 126 is the neutron number. Now, what is the importance of these numbers, magic numbers? We call them as the magic numbers. Just like electrons are paired in the electronic shells, nucleons are also paired in the nucleonic shell. And when they are paired, they are found to be stable. And one rule was proposed that is called Arkin's rule. Arkin's rule. Arkin's rule. According to this rule, the nucleus having the even number of protons or neutrons or both are found to be stable and having maximum number of stable isotopes compared to the odd number of protons and neutrons. That generation is called Arkin's rule. So it is really mystery to understand the very structure of the nucleus, and these numbers, magic numbers, indicate the shell capacity, nucleonic shell capacity of the nucleus. The last aspect of discussion regarding the relative stability is the meson theory. In 1935, Japanese scientist Yukawa proposed this meson theory. Mesons are the short-lived particles which are resulted during the interaction of proton and neutron within the nucleus. They exchange between proton and proton, neutron and neutron, and proton to neutron and neutron to proton. Hence, they are called exchange integrals. In the process of exchange, they bind these nucleons. Say that is the neutron to proton, negative. Dotted lines indicate the binding forces, and proton to neutron pi positive. This is the pi meson negative charge, positive charge, and neutron to neutron pi neutron. Proton to proton pi neutron. So these bind, and among these, say, 4 combinations of attractions by the 5 mesons, and neutron and proton, all combinations of this. You take this as an example, the very stable nuclei, and also deuterium 1. Here 1 neutron, 1 proton is present. This is the highly stable. Then we can expect neutron to proton, proton to neutron binding force are very strong compared to others. Based on this, of course, we cannot generalize with this. So these are the different aspects of discussion of relative nuclear stability. Now, once we discuss the relative nuclear stability, what we have understood that beyond the atomic number 82 and beyond the mass number 230, they are found to be radioactive nuclears. They emit, they spontaneously disintegrate and tend to attain the stability and ultimately fall into the zone of stability. So then we need to discuss the next one, phenomena of radioactivity. Radioactivity is a phenomena of spontaneous disintegration of nucleus of different elements by emitting alpha, beta and gamma particles. So that spontaneous disintegration, spontaneous emission, this was first proposed in 1896 by Henry Becquerel. And Madame Curie in 1911, Madame Curie discovered the polonium and radium elements. Now, if you really see the radioactivity phenomenon, as I mentioned just now, if the radioactive substance is taken in the wooden box and rays are emitted, and these are the gamma rays, beta, these are alpha rays, beta rays. These three rays are found based on the placing of the magnetic field. This is negative charge, this is the positive charge plate. This clearly indicates that gamma rays do not have any charge. Alpha rays have the positive charge based on bending nature, and based on the bending nature of beta rays, they are supposed to have the positive charge. Now briefly we'll discuss the properties of alpha, beta, gamma rays in various aspects. First, alpha rays. Better we'll discuss in comparative aspect. One is the nature, alpha, beta, gamma rays. These are the positively charged particles, negatively charged particles, not having any particles. These are the particle nature photons are present. That is nothing but the light. Next, source. As I mentioned, lower mass number nuclei, low n by population nucleus, low n by population nucleus, high n by population nucleus emit this radioactive. So they are radioactive nucleus. And here gamma rays source is after emission of alpha or beta, gamma rays may be emitted. Gamma rays may be emitted. Third one is the velocity. So the 1/20th to 1/15th of light velocity, this is 33% to 90% of light velocity. Low velocity beta rays are called soft beta rays. high velocity beta rays are called hot beta rays. And this is the light velocity, since it is light. Representation. Here, these are the particles, particle rays. It is represented with a helium nuclide or simply alpha. It is represented with a electron or simply beta particle. This is the, of course, the zero mass, zero atomic number mass number. Penetrating capacity. These penetrate up to 0.01 mm of aluminum sheet. This is 5 mm of aluminum sheet. 25 centimeters of aluminum sheet. So naturally the penetrating capacity of gamma rays is very, very ionizing nature. Ionizing nature. Ionizing nature depends on the momentum of the particle. Very, very high ionizing, very, very high because of high momentum. When these rays are passed through the, say, medium, gas, the electrons of the atoms or molecules which are knocked off. Very high, moderate, and very low. Nearly 100 times greater than the beta particles. Here, effect on zinc sulfide screen. Luminescence is noticed here and sparking is noticed. Based on that only we can identify the number of alpha particles. Similarly, here also number of beta particles emitted. So that is the luminescence nature. Luminescence nature is found in both cases. Here it is not found. It is found, but very, very less significant in this case. So sparkings are noticed. Based on that, the number of alpha particles and beta particles are identified. And the experimental methods which are used to identify the alpha, beta, gamma rays are the spinthariscope and Geiger-Müller counter, spinthariscope, Geiger-Müller counter, and Wilson cloud chamber. These experimental methods are used to identify the falling of alpha, beta, gamma rays. One thing we can notice among these gamma rays are found to be very toxic in nature when they fall on the living cells. So gamma rays which I mentioned, it's the after effect of alpha, beta, gamma rays. Hence, it is not the compulsory condition for the emission of gamma rays from radioactive nuclears. Hence, we have to redefine the radioactivity phenomenon. It is the phenomena of, it is the spontaneous phenomena of emission of alpha or beta and gamma. So here, as we have seen that alpha emission is only from certain characteristic nucleus. Beta particles are emitted only from some characteristic nature. After this, gamma may be emitted or not. So one example I can mention that will explain the very origin of gamma rays. Origin of gamma rays. For example, from uranium-238 So if at all alpha particle is emitted, thorium daughter nuclei may be in the ground state or excited state. Say the excited state, we can describe in terms of the star. The relationship between these two dot nucleus is the nuclear isomers. So if it is excited, in other words, if alpha particle with the kinetic energy of 4.18 and such daughter nucleates are in the ground state, if alpha particle kinetic energy is in the 4.13 million electron volts, this is in the excited state. So excited state will come back to the ground state, and here the thorium 23490 star to the ground state 90 plus 0.05 million electron volts amount of energy is emitted in the form of light that falls in the gamma region of the electromagnetic spectrum. So one important thing we have to notice during the nuclear decay with the different possible particles emission, here radioactive nucleus isotope is resulted by the emission of one alpha particle and followed by two beta particles. This we can understand taking the 212 lead 82. If this beta particle is emitted 83 this month, M212 as you know. First, no. Generally, we take X, say, Z, A, one alpha particle is emitted. This is naturally Y, Z minus 2, A minus 4. A minus 4, Z minus 2, now beta particle is emitted. Say, two beta particles. Z is retained, naturally X. Now the A minus Z. The relationship between this and this isotopic relationship. So, one alpha followed by two beta particles isotope is resulted. And which I discussed isobar in many beta emission, isobar is resulted. And neutron capture proton emission, isobar is resulted. In many cases, isotone is resulted during the positron emission. So such aspects are already mentioned. Group displacement. This was proposed by three scientists, Azam, Russell, and Sari, independently. This is generalization only. When alpha particle is emitted, as we have seen that the X, Z, A, alpha particle is emitted, daughter nuclear portion in the periodic table is displaced by 2 units. So its position displaces to the left hand side by 2 group years. So if beta particle is empty, say some A, say if beta particle is empty, that is nothing but an internuclear electron. So B, proton number increases, its daughter nuclear position moves right hand side by 1 unit. This is called group displacement law. Radioactive series. Natural radioactive elements disintegrate one after another. If the daughter nuclide is found to be unstable and found to be radioactive, again it disintegrates. This disintegration process in consecutive manner till very stable nucleus is formed. In which number of steps are there? If you really see the pitch blende ore of the uranium, in which the number of nucleides which are present, and also the very stable nucleide is the lead-206 isotope. That is the last nucleide which is found to be stable. Up to then, 16 radioactive nucleides are which are found in the pitch blende ore. Means 16 steps are involved. So that sequence of decay process called radioactive decay process, and all the nucleides which are present in the one given series having unique nature. In the case of the thorium, the nucleides mass numbers are divisible by 4. In the case of uranium, the remainder is, say after they are divisible and remainder is 2, hence 4n plus 2 series. Thorium is the 4n series, and neptunium in this case the remainder is 1, that is 4n plus 1. In the case of the actinium, the remainder is 3, 4n plus 3 series. So 4 different series, 4n series, 4n plus 1 series, 4n plus 2 series, 4n plus 3 series. This is the thorium series, the starting and ending nucleide. We can mention here thorium, this is a neptunium series, this is the uranium series, this is the actinium series. Thorium 232, 90, ending with the actinium 8, 82, neptunium 93, 237, lead 209, bismuth 83, this is uranium 92, 238, and lead 206, 82, this is actinium 227, 227, 89, lead 207, 82. Peculiarly see that this case is the artificial radioactivity, where the nucleides all are man-made elements. These are 3, 4n, 4n plus 2, 4n plus 3 are the natural radioactive series. This we can easily witness in the respective ores, where end stable nucleide is found to be lead-208, in this case pitch blende ore 206, and actinium ore 207. So the consecutive series we expect, depending upon their half-life period, left to right, half-life period increases, that indicates the stability increases. And we can hypothetically found how many alpha particles, beta particles emitted in a given series. Taking the thorium as an example, 90 to 32, and the daughter nuclide, lead 208 and 82, number of alpha particles A. Alpha particles represent the helium nucleus, number of beta particles represented with the electron. Now to find out the number of alpha particles, it is very easy to compare the mass numbers. 208 plus 4A, that is 0, and 4A, 232 minus 208 is a 24. So A 24 by 4, 6 alpha particles. Similarly, beta particles can be found where compared with the atomic numbers. Here 2A means 12 minus B. So this is B is what we get 4 beta particles. Like this we can hypothetically estimate the number of alpha particles emitted and beta particles emitted in a given series, providing the initial nucleate and final last nucleate. Thank you.